Everything that has ever existed or will exist blasted into creation 13.8 billion years ago, from a point smaller than the period at the end of this sentence. But here's something that will blow your head. We're going to embark on an impossible voyage into the realm before that moment when nothing wasn't empty, time didn't tick, and the whole concept of existence vanished. Breaks down totally. We'll examine into quantum foam bubbling with virtual particles, the limitless multiverse, colliding and mathematical realities that make our reality appear tiny. If you're ready to rethink everything you believe you know about reality, click the like button and subscribe. Prepare yourselves. We begin. Imagine the ultimate deadline. Scientists refer to the literal end of the past and the beginning of the future as T0. Yet that simple moniker conceals the most dramatic shift in cosmic history. At this point, the concept of before is irrelevant because time does not yet exist. Think about it for a second. There are no ticking clocks, aging, sequences of events, darkness, or waiting for light. Only the entire lack of duration itself. The mathematics break down here, like a computer dividing by zero. Einstein's equations, which describe gravity and space-time with flawless precision everywhere else, simply cease to function. They generate infinities and inconceivable answers, as if the universe has a "do not enter" a sign written in the language of physics. But this is where things get really bizarre. The moment we're seeking to comprehend isn't simply the start of our universe. It marks the start of the framework that allows for new beginnings. Before this moment, there was no stage for any cosmic drama to play out on. No dimensions to measure, no space to fill, and no time to wait. Consider describing the hue of something that has never reflected light in an environment where light is unattainable. That's what we're aiming at when we question what happened before the Big Bang. We're utilizing notions that only make sense after the event we're examining. However, contemporary physics reveals that something significant was happening in this inconceivable reality. According to quantum theory, even in complete nothingness, energy can briefly appear and then disappear. These quantum fluctuations occur frequently in the vacuum of space now, but they might also occur in utter nothingness. So maybe nothing was never absolutely nothing at all. According to the leading theory, our entire universe began as one of these quantum fluctuations, but instead of evaporating, it expanded in less than a trillionth of a second. This minuscule bubble of energy expanded faster than light, generating space along the way. Imagine a soap bubble developing on the surface of totally motionless water. But the water does not exist. The surface doesn't exist, yet the bubble creates both. As it expands, the bubble encompasses the entire pond, globe, and everything. This process, known as cosmic inflation, explains why our universe appears to be uniform in all directions. It also explains why space appears flat rather than curved, but it creates an even more perplexing conundrum, which physicists are still grappling with today. If quantum fluctuations can generate a cosmos from nothing, why should they stop there? The math says they wouldn't. They imply something considerably more amazing than a single cosmic beginning. Yet what comes next makes our Genesis story appear straightforward. When you entirely empty a jar, is it truly empty? Most people would agree, but physics shows something startling. What we consider empty space is actually alive with invisible movement. Even in the darkest vacuum between galaxies, when matter is scant, 1 atom per cubic meter of space may still be alive with energy. This isn't the kind of nothing that philosophers argue about. This is observable, detectable, experimentally confirmed nothingness that refuses to remain nothing. Scientists discovered this when they attempted to chill things to absolute zero and extract every last bit of energy from a system. They discovered something impossible. Even at the lowest feasible temperature of 460 degrees Fahrenheit, the energy never drops to zero. Quantum fields continue to oscillate with zero-point energy, as physicists define it. It's like trying to calm a kettle of boiling water. No matter how much heat you remove, small bubbles continue to form and erupt at the bottom. These quantum fields fill every cubic inch of space, resulting in what scientists term the quantum vacuum. Consider an ocean that appears to be absolutely peaceful on the surface, but is actually somewhat turbulent beneath the waves. Countless organisms swim in patterns too fast and small for your eyes to detect. The quantum vacuum operates in the same way, looking empty, yet constantly creating and destroying at scales smaller than atomic. Here's where things become weird. These quantum fields can draw energy from the future. Plans include creating couples of particles that appear, dance briefly together, and then annihilate and disappear. This occurs trillions of times every second in every tiny volume of space surrounding you. Right now, the borrowed energy is returned so swiftly that the universe's accounting system never notices. The debt scientists prove this isn't just theory by measuring the Cassie effect, which occurs when two metal plates are placed incredibly close together in a vacuum, giving the quantum fields between them less opportunity to change than the fields outside. This results in a small but noticeable force pushing the plates together. Empty space literally creates pressure. But this is what will make your head spin. If our visible cosmos emerged from quantum fluctuations in a vacuum, where was that vacuum? What made the quantum fields able to fluctuate in the first place? We are obliged to consider whether deeper layers of nothingness exist. Some physicists argue that mathematics, rather than numbers printed on paper, may be the foundation of everything, consisting of pure mathematical relationships that exist independently of physical reality. According to this viewpoint, our cosmos is composed of mathematical patterns that are complex enough to experience themselves rather than matter and energy. Others argue that consciousness plays an important part in creating reality through observation. According to quantum mechanics, particles can exist in several states at the same time until they are measured. Could the act of observation by conscious creatures possibly fail? Infinite possibilities into the single reality that we experience. These considerations lead us to consider an even wilder possibility. What was before existence? Particles are currently appearing and disappearing inside your body. These are not sci-fi special effects. They're virtual particles that are essential to how reality functions. At the most fundamental level, quadrillions of these phantom beings emerge from your cells every second, live for inconceivably short periods of time before disappearing completely. Virtual particles may sound like fantasy, yet they create actual, observable results. They control the magnetic characteristics of electrons, how light interacts with matter, and even the force that prevents atomic nuclei from floating overhead. Atoms cannot exist in the absence of virtual particles. Chemistry would be impossible, and you wouldn't be present. Think of virtual particles as cosmic credit cards. They draw energy from the quantum vacuum, spend it momentarily to exist, then repay it by disappearing. The shorter their lives, the more energy they can borrow. Some virtual particles only live for 10 to the negative 24 seconds, but in that incomprehensibly tiny time, they can transport vast amounts of energy. The quantum vacuum is not just an empty space waiting to be filled. It's more like a cosmic soup, with elements continually dissolving and reforming. Virtual photons transport electromagnetic forces between charged particles. Virtual gluons hold quarks together within protons and neutrons. Virtual particles of all kinds pop in and out of existence, forming an invisible basis beneath visible reality. Here's the mind-bending portion. These imaginary particles can occasionally become real. When sufficient energy is pushed into the quantum vacuum, virtual particle pairs can separate before annihilating each other and becoming permanent contributions to reality. This occurs near black holes, where powerful gravitational fields supply the energy required for virtual particles to escape their quantum debt. Stephen Hawking observed, that black holes evaporate by transforming virtual particles into physical particles at their event horizon. Gravity separates virtual particle pairs. One particle goes into the black hole, while the other escapes into space as actual radiation. The black hole loses energy as it shrinks, eventually disappearing in a final flare of light. This method implies something substantial: the nature of existence. If virtual particles can become real when given enough energy, and our entire cosmos may have originated as a quantum fluctuation, the line between real and virtual becomes startlingly thin. Some physicists argue that our entire world may still be virtual in some sense, drawing energy from an even deeper level of reality that we have yet to uncover. Everything we refer to as real, according to this viewpoint, planets, people, and galaxies, exist on borrowed time in a cosmic quantum fluctuation that began 13.8 billion years ago. However, if virtual particles are capable of generating our universe, they may also construct others. The quantum vacuum that creates transitory virtual particles around us may also create vast cosmos in realms. We cannot discern the ramifications of this revelation. Lead us to a potential that outshines even our cosmic origins. Our universe may be one bubble in an endless cosmic bath right now, and while you read these words, countless other versions of you may be reading slightly different versions of the same line. Some parallel universes are essentially identical to our own, differing only by the position of a single electron. Others are so out of the ordinary that the laws of physics do not apply. When physicists discovered that quantum fluctuations didn't have to end with the creation of one universe, they developed the multiverse theory. If the quantum vacuum can construct our universe, it can create others. In fact, the mathematics suggests that it must make others indefinitely, similar to soap bubbles developing on the surface of an infinite sea. Each universe would start with its own Big Bang, expand through its own type of cosmic inflation, and evolve its own distinct characteristics. Some may have more gravity, causing stars to burn faster and die earlier. Others may have weaker electromagnetic forces, prohibiting atoms from forming at all. Most would be sterile wastelands with no complexity, but a handful could support life. We can't envision an infinite cosmic ocean with every imaginable wave. Our cosmos is but one wave in this ocean, temporary and unusual, but not exceptional. The multiverse does not care about our existence any more than the ocean does about individual drops of water. But here's when it becomes absolutely amazing. Some variants of multiverse theory propose endless worlds, implying that every potential variety of reality occurs somewhere. There is a universe in which dinosaurs never became extinct. There is a universe where gravity repels rather than attracts. There is a universe in which you chose to become an astronaut rather than reading this script. These alternative realms are not sci-fi fantasy. They follow naturally from our best mathematical explanations of quantum mechanics and cosmic inflation. When you solve the equations that govern the quantum vacuum, limitless universe formation emerges as an unavoidable concept. The consequences are both stunning and terrible. If there are infinite worlds, then every tragedy and success is taking place right now. Every book that could be written already exists somewhere in the universe. Every scientific discovery that may be made has already occurred in innumerable parallel universes. Some physicists take this theory even further, implying that the multiverse is merely one rung in a much larger hierarchy. Maybe there are endless multiverses. Each contains infinite universes, nested in layers of reality that are beyond our comprehension. However, if parallel universes exist, they may not always be parallel. Quantum mechanics predicts that universes may clash, merge or influence each other in ways we are only beginning to grasp. The cosmic microwave background radiation that covers our sky may carry faint traces of collisions with other universes billions of years ago. This possibility suggests an even more extreme notion of what existed But, for the beginning, what if our Big Bang was not the start, but rather the latest restart? Consider a cosmic phoenix that dies in flames every trillion years, only to rise from its own ashes. Some physicists believe that our cosmos follows this pattern, going through unending cycles of expansion, collapse, and rebirth. According to this viewpoint, the Big Bang was a metamorphosis of something that came before, rather than a creation from nothing. The cyclic universe concept proposes that our universe has expanded for billions of years, just as we see now. However, the expansion gradually slows, stops, and reverses. Gravity wins the ultimate battle, bringing every galaxy, star, and atom back together in a cosmic collapse known as the Big Crunch. But here's a twist. Instead of resulting in total devastation, the tremendous crunch produces a big boom. The universe recovers from maximum compression, bursting into a new cycle of expansion. Time does not stop during this changeover. It continues through what physicists refer to as a cosmic bounce. Think of it as a cosmic trampoline. Our universe is falling toward the trampoline surface, speeding as it nears maximum density. The trampoline's elasticity then kicks in, sending the universe back into another cycle of expansion. Each bounce produces what appears to be a loud bang from the inside, but it's actually simply another oscillation in an everlasting pattern. This approach solves various problems with standard Big Bang theory. It explains why our universe appears so homogeneous in temperature and density without necessitating the extremely rapid inflation that standard models require. It also answers the unpleasant question of what caused the Big Bang. As there was no ultimate beginning, only unending cycles. Recent discoveries of our universe's accelerated expansion, caused by unexplained dark energy, appear to rule out a future grand crunch. However, cyclic theorists have updated their models to include dark energy. They propose that the strength of dark energy varies over cosmic timescales, gradually reversing from expansion to contraction to drive. In some forms of cyclic cosmology, each cycle lasts approximately 1 trillion years. Our present cycle began 13.8 billion years ago, so we are very young in cosmic terms. We have hundreds of billions of years before the expansion stops and collapse occurs. However, each cycle may not be similar. Small changes could build throughout cosmic generations, resulting in each universe being slightly different from its predecessor. Perhaps consciousness and intelligence evolve further with each cycle, as information is passed down from one cosmic generation to the next. According to cyclic models, parallel worlds grow and shrink in turn, much like cosmic pistons in an infinite engine. While our universe grows, others constrict, and some burst into new huge bangs. We're coasting through our expansion period. These concepts suggest that the question of what came before the Big Bang has a simple answer in the prior cycle, but this only deepens the puzzle. What caused the ceaseless cycling in the first place, and will the cycles ever end? Every point in space may be surrounded by 6 invisible dimensions. Right now, as you read this, you are surrounded by dimensions you cannot see, touch, or experience firsthand. According to string theory, these hidden dimensions are wrapped up so tightly that they can be found anywhere in our familiar 3-dimensional reality. However, it scales so small that even the most powerful microscopes cannot identify them. Consider a garden hose seen from afar. It appears one-dimensional, like a line. But zoom in close, and you'll notice it contains hidden circular dimensions wrapped around its length. String theory argues that our universe operates in the same way. What we perceive as 3 dimensions of space plus 1 of time may actually be 4 dimensions unfurled from a reality with 10 or 11 total dimensions. These additional dimensions are not empty space. They are dynamic shapes, fluctuating arenas in which the fundamental forces of nature demonstrate the strength of gravity. Electromagnetism and nuclear forces in our known dimensions are determined by how the hidden dimensions are curled and twisted. String theory proposes that the smallest building blocks of reality are tiny vibrating loops of energy known as strings. These strings are incredibly short, ranging from 10 to 35 meters in length. That's so minuscule that even if you scaled one atom up to the size of our solar system, a string would be smaller than a tree. Each different vibrating pattern of these strings results in what we see as distinct particles. An electron is a thread that vibrates in one direction. A photon is the same string that vibrates differently. A quark is another vibration pattern. It's like a cosmic symphony with each note representing a different fundamental particle. But here's how it relates to our cosmic origins. String theory argues that the Big Bang was caused by collisions between higher dimensional objects known as branes. Our entire universe could be a three-dimensional membrane suspended in higher dimensional space, similar to a soap coating on the surface of a multidimensional bubble. When two branes collide in this higher dimension, massive amounts of energy are released into each brane. From our perspective, the energy release inside one of these branes appears to be a tremendous bang. Time and space, as we know it, began at the point of collision, yet the branes existed prior to the crash. This brane collision hypothesis explains various riddles concerning our universe's origins. It explains the remarkable uniformity of cosmic microwave background radiation without requiring faster than light inflation. It also implies that what we call the Big Bang was essentially a transition from one brane state to another, rather than creation from emptiness. Parallel branes hosting other worlds may also exist in the hidden dimensions. These parallel realities may be as close as a millimeter away from us in higher dimensional space, but they are utterly out of reach since we are confined in our three-dimensional brane. This opens up even more mind-bending possibilities about the nature of cosmic creation. Every second, a new universe is created somewhere in the cosmos. While you were reading this script, numerous huge explosions exploded in remote regions of space, each one resulting in an entire cosmos populated with billions of galaxies. This is not science fiction. It is the logical conclusion of everlasting inflation hypothesis. Traditional inflation theory, one of the most successful models in modern cosmology, explains how our universe rose from subatomic to cosmic scale during the first fraction of a second. However, everlasting inflation implies that this process will continue indefinitely. It simply goes from place to place, creating an infinite number of pocket worlds in an ever-expanding multiverse. Imagine a saucepan of boiling water with bubbles constantly forming and separating from the surface. Each bubble represents a universe similar to ours, with its own space, time, and physical laws. The boiling water represents the inflating field that fills the multiverse indefinitely, forming new bubbles of reality. Our observable cosmos is only the interior of one such bubble. The Big Bang was not the start of everything, but rather the moment when our small region of space stopped expanding and began the slower expansion we see today. But outside our bubble, the cosmic inflation field continues to grow exponentially, occasionally creating new pocket worlds. This process has no origin or end, even if inflation began at some point in the past. Once it starts, it generates endless future time and space. The multiverse expands so quickly that no matter how many pocket universes emerge, there is always room for infinitely more. Each pocket universe may have distinct physical constants, such as higher gravity, that causes stars to burn out quickly. In others, the electromagnetic force may be weaker, prohibiting complicated chemistry. Most pocket universes would be sterile, but one or two would have the necessary conditions for life to flourish. The distances between pocket universes are astonishing beyond belief. They are separated by regions of still inflating space that expand faster than light can travel through. Even if you could travel at light speed indefinitely, you would never reach another pocket universe since the distance between you and it grows faster than you can cross it. But here's the genuinely mind-bending part. In an ever-expanding multiverse, Every potential world exists somewhere. There is a pocket world, where the laws of physics permit faster-than-light travel. There's another in which time reverses. There is even one in which the constants are so perfectly calibrated that black holes grow into aware creatures. This limitless number of realities raises serious issues regarding the nature of existence itself. If every imaginable universe exists, the terms possibility and actuality become synonymous. Everything that can happen occurs somewhere in the everlasting multiverse. Some physicists believe that everlasting inflation makes science impossible by implying that anything can happen anywhere. Others consider it as the most elegant explanation for why our cosmos appears to be well designed for complexity in life. However, even everlasting inflation leaves a larger riddle unresolved at the edge of the Big Bang. Mathematics itself breaks down. Physicists have traced our universe's history back to just a fraction of a second after the Big Bang. They can explain the formation of the first atomic nuclei and the birth of the earliest stars. Even when space became transparent to light, there was one boundary they couldn't cross: the instant when all of their equations produced nonsense. This boundary is known as the Planck epoch, and it lasts from time 0 to approximately 10 to the negative 43 seconds after the Big Bang. During this incomprehensibly brief period, the cosmos was so hot and dense that quantum processes overpowered gravity itself. Space and time were blurry and ambiguous, as if a snapshot had been magnified to the Planck scale, revealing individual pixels. The seamless fabric of space-time that Einstein described is ripped into quantum foam. Distances less than the Planck length, ranging from 10 to 35 meters, become meaningless. Time intervals are shorter than the Planck time. It is impossible to measure between 10 and 43 seconds, even on principle. Consider using an atomic ruler to measure anything smaller than an atom. The ruler becomes the limiting element. Similarly, when we attempt to investigate the Planck epoch, our understanding of space and time becomes a constraint. We're attempting to use space-time to discover the origin of space-time itself. This generates what physicists refer to as the boundary problem. Every physics equation implies the existence of space and time as a background stage on which events can take place, but there was none at the time of the Big Bang. The stage was being built together with the principles of moment and creation. Einstein's theory of general relativity, our best theory of gravity and space-time, predicts that all stuff was crushed into a mathematical point of infinite density known as a singularity. However, in physics, infinities typically indicate that a theory has hit its limit. Reality does not contain infinities. Our mathematical descriptions just break down. Quantum mechanics advises that the singularity be replaced with something else, perhaps a place with the highest possible density, where space and time are quantized like energy levels in an atom. However, there is currently no complete theory of quantum gravity to characterize this region. Some physicists argue that asking what happened before the Planck epoch is akin to asking what's north of the North Pole. Time itself may have a limit, a first moment that was not preceded by anything in this view. The Big Bang marks the definitive beginning of temporal existence. Others propose that time may develop from more fundamental, timeless processes. Temperature comes from the motion of innumerable atoms, while time may develop from quantum interactions in a deeper reality without duration. This boundary problem points to one of science's fundamental mysteries: the link between information and existence. Where did the knowledge required to create the universe come from before it existed? Every particle in your body, every atom in every star, and every quantum state in every galaxy holds information. Your DNA encodes information about your biological structure. The quantum states of electrons in your brain include information about your thoughts and memories. The universe is primarily composed of information, but where did it all come from? Originally? Consider a simple hydrogen atom, the most fundamental element in the universe. Even this seemingly basic system provides exact information on the electron's energy level, spin direction, and orbital properties. Multiply this by every atom in every galaxy, and the amount of information in our observable world explodes beyond comprehension. Traditional physics views knowledge as something that is embedded into existing matter and energy, whereas quantum mechanics shows something unusual. Information itself may be more fundamental than the stuff and energy that transports it. In quantum systems, information about a particle's state defines what the particle is, not vice versa. This creates a paradox that gets to the heart of cosmic origins. If our universe originated from quantum fluctuations in empty space, where did the information contained in those fluctuations come from? Empty space should not contain the massive libraries of data required to characterize the attributes of billions of galaxies. Some scientists argue that information, like energy, is conserved, which means it cannot be created or destroyed, only transformed. In this opinion, the information in our universe had to exist in some form before the Big Bang, but this only adds to the mystery. What stored everything? Our cosmos represents one possible arrangement of this basic knowledge chosen by processes. We do not yet grasp this information. The first view of reality refers to an even crazier possibility regarding the nature of existence itself. True nothingness may be unattainable. Consider complete emptiness. No matter, no energy, no space, no time, no fields, no forces, and no possibility for anything to happen. This is commonly referred to as total nothingness, yet quantum mechanics indicates that such a state cannot exist in theory. The reason is the uncertainty principle, which is one of the fundamental rules that regulate reality at the smallest scales. This principle asserts that no particle's exact position and momentum can be known at the same time, although it relates to more than just particles. It also applies to energy, time, and the quantum fields that make up all of space. In a fully empty location with zero energy, you would know exactly how much energy there is. However, the uncertainty principle prevents this perfect knowledge. As a result, the energy must fluctuate, borrowing from and repaying the quantum vacuum in an endless cosmic shell game. These variations are not simply mathematical artifacts. They produce real-world effects. Virtual particles persist for a brief period of time, then annihilate each other and vanish. The greater the variation, the shorter the lifetime. However, borrowed energy can generate temporary realities for a short period of time. Here's where things get very crazy. If quantum fluctuations can occur in empty space, then they should be possible in the absence of space. Absolute emptiness. If it could exist, it would be susceptible to quantum uncertainty. This means that emptiness would fluctuate, generating something from nothing using the fundamental laws of quantum mechanics. These variations in absolute nothingness would not be restricted to small particle pairs. The uncertainty principle allows for large fluctuations to occur over extremely short periods of time. A fluctuation large enough to create an entire universe is permitted as long as it pays back. It borrows energy quickly enough, but this is where cosmic inflation comes into play. If the universal fluctuation expanded rapidly enough, it may exceed its own quantum wavelength before the payback period expired. Once this occurs, the fluctuation is real and lasting, transitioning from borrowed existence to actual existence. Consider it a quantum credit card that has no spending limit but requires instant payment. Most transactions are immediately retracted, but every now and then, a purchase becomes so huge that the system is unable to reverse it. The debt becomes real, as does the purchase. Our entire cosmos could be the outcome of a quantum fluctuation that became too large to reverse. According to this viewpoint, existence is a kind of cosmic accident, a quantum blip that swelled past the point of no return. However, if one universe can emerge from nothingness, others should do the same on a continuous basis. If pure nothingness existed, it would be fundamentally unstable, resulting in an infinite number of realities due to quantum uncertainty. This poses an important question. If nothingness is impossible, has something always existed? The answer prompts us to investigate the role of consciousness itself. What if the cosmos requires observers to exist? Quantum mechanics provides us with a dilemma that has perplexed physicists for almost a century. Before measurement, particles exist in numerous states and are spread out in clouds of possibility. However, when someone examines them, these possibilities transform into distinct realities. The act of observing literally shapes the reality being witnessed. This is not philosophy, it is experimentally confirmed science. Electrons can exist in numerous locations at the same time until they are detected. Photons can take several pathways before being measured. The quantum universe is basically ambiguous, unless consciousness examines it. But here's a thought-provoking question. If observation generates reality, what observed the world before conscious beings evolved? How did the universe survive for billions of years before the first minds arose, transforming its quantum possibilities into concrete states? Some scientists argue that consciousness itself may be basic to the universe, not something that evolved from complicated arrangements of matter, but something that existed from the beginning. According to this theory, the Big Bang was more than simply the formation of matter and energy. It was also the first time cosmic consciousness began to observe itself. Think of reality as a massive quantum computation. Without awareness to operate the software, the universe would remain a cloud of unrealized potential, suspended in quantum superposition indefinitely. This theory proposes that what existed before the Big Bang was pure consciousness without content, infinite potential awareness with nothing to be aware of. The Big Bang would represent the moment when consciousness began to observe itself, thereby creating space, time, and matter through the act of self-observation. But what if consciousness produces reality through observation? Then different types of consciousness may produce distinct kinds of reality. Human awareness, with its distinct patterns of attention and measurement, alters the universe in ways that mirror our cognitive architecture. Alien consciousness with different sensory systems and mental processes may witness a fundamentally different cosmos come into existence. This opens up remarkable potential for alternate universes. Every conscious action you make has the potential to split the cosmos, generating branches where multiple options can play out. Every observation you make may select one reality from among myriad quantum alternatives. Your consciousness does more than merely witness the universe. It also contributes to its creation moment by moment. Some interpretations of quantum mechanics propose that all conceivable realities exist concurrently in a wide multiverse, but awareness chooses which branch to experience. Prior to the Big Bang, all possible worlds existed in pure potential. The emergence of awareness resulted in the first definite reality by choosing one option from an infinite quantum menu. If awareness is basic rather than emergent, it may be the one thing that does not require creation or explanation. It is simply like existence itself. The universe could be consciousness discovering its own limitless potential through the experience of space, time, and matter. This opens up even more radical possibilities about the relationship between mind and mathematics. What if reality is literally composed of mathematics? Right now, you might believe you're reading words made of matter, sitting on a physical chair, and inhaling actual air. However, the mathematical world hypothesis proposes that you are perceiving mathematical structures that are so sophisticated that they are self-aware. You are not composed of atoms or molecules. You're made up of numbers and equations that have come to believe this isn't a metaphor or analogy. Max Tegmark, an MIT physicist, genuinely believes that mathematical and physical existence are same. Every electron, photon, and quantum field is essentially a mathematical entity. The universe does not just follow mathematical laws, it's maths. Consider what mathematics truly represents. When you use mathematics to describe motion, You are not making an approximation to reality. You are uncovering the true structure of reality itself. The equations do not describe something else. They are something else. Physical objects are mathematical objects that are complicated enough to interact with one another. This concept answers a problem that has perplexed scientists for ages. Why is mathematics so efficient in explaining the natural world? The solution is straightforward. Mathematics works flawlessly because reality is mathematical. We are not discovering mathematical approximations for physical laws. We are uncovering the mathematical underpinnings that underpin existence itself. But this is when things start to get really interesting. If our universe is a mathematical structure, then every potential mathematical structure should have a physical counterpart. There is a world based on alternative geometries, with space having 4 dimensions rather than 3. There is a universe in which the mathematical constants have various values, causing physics to function differently. Every mathematical theorem, equation, and logical system corresponds to a physical universe, somewhere in the collection of all mathematical realities. Our universe is described by the specific mathematics we perceive, but there are innumerable more universes described by alternative mathematics. According to this theory, the Big Bang did not create matter and energy out of nothing. It was the point at which a certain mathematical structure became complicated enough to accommodate observer moments, which are conscious experiences contained within the mathematical framework. You are not a biological being viewing a mathematical universe. You are a mathematical pattern that has become self-aware. This explains what was prior to the Big Bang. Mathematics existed in all of its infinite intricacy and possibilities. The ensemble of all mathematical structures was complete and eternal, with every possible universe as a subset. Our Big Bang reflects the moment when observers initially arose within a specific mathematical structure. Time itself becomes an illusion. In this view, the mathematical structures that make up reality endure indefinitely. We experience time because we are immersed in structures that contain temporal sequences, similar to geometric theorems, but all moments exist simultaneously outside the structure. According to the mathematical world idea, consciousness is not something independent from mathematics, but rather the internal experience of sophisticated mathematics. When mathematical systems get sufficiently complex and self-referential, they produce subjective experience. This forces us to address one of the most profound riddles in all of cosmology. Dark energy should not exist, yet it is pulling our cosmos apart. In 1998, astronomers made a groundbreaking discovery that changed everything. Physicists believed they knew about cosmic destiny. The universe's expansion was accelerating rather than slowing down due to gravity. Something was driving galaxies apart with growing force, and no one knew what it was. They termed this enigmatic force dark energy, and it accounts for around 70% of all that exists. Dark energy is unseen and undetectable, save for its impact on cosmic expansion, and it entirely contradicts our idea of how energy should behave. Normal energy is diluted as space expands, much like scent spreading over a room. Dark energy grows stronger. The prevailing explanation is based on the cosmological constant. Einstein assigned a number to his equations to keep the universe steady. When observations revealed that the cosmos was expanding, he described it as his worst blunder. However, the recent discovery of accelerating expansions implies that Einstein's gaffe was a deep insight into the nature of reality. The cosmological constant represents the energy density of empty space. Even a perfect vacuum contains energy, which generates a repulsive force that pulls space apart. It's as if the universe contains an invisible substance that causes space to expand. But here's the problem that keeps physicists up at night. When you use quantum mechanics to calculate how much vacuum energy empty space should contain, the result is 10 to the 120th power, greater than what we experienced. That's not a little mistake. It is the worst scientific prediction ever made. If quantum mechanics is correct regarding vacuum energy, our cosmos should be expanding at such a rate that atoms, stars, and galaxies would not be possible. The fact that we are here to raise these questions indicates that the cosmos has calibrated its vacuum energy to a specific number, very near to zero, but not exactly zero. This delicate adjustment is quite precise. It seems implausible that it happened by chance. It's like balancing a pencil on its point for billions of years as earthquakes rock the table, but somehow, the universe has achieved an inconceivable balance. Some physicists argue that what we call dark energy is actually a different field that replicates the effects of the cosmological constants. Others argue that the principles of physics themselves may evolve throughout cosmic time. With the cosmological constant changing, as the cosmos ages, the multiverse provides an alternative explanation. If infinite universes existed with differing vacuum energies, most would expand or collapse too quickly for complexity to evolve. We see a universe with the correct cosmological constant because we couldn't exist in universes with the incorrect value. However, this presents an even deeper question. Why do nature's fundamental constants appear to be ideally calibrated for complexity, consciousness, and life? The answer could reveal the most profound secret about what came before our cosmic genesis. The energy that is destroying our universe could be a remnant of its creation. Dark energy remains the greatest mystery in modern physics, but its birth tale may be written in the early moments following the Big Bang. Some physicists argue that dark energy is essentially fossil energy. From cosmic inflation, the rapid expansion that stretched our universe from subatomic to cosmic size in the first fraction of a second, space itself expanded faster than light, propelled by a quantum field known as the infall. When inflation halted, this field possessed massive energy density, enough to form all of the matter and energy we observe today. But what if inflation never really ended? What if a minuscule portion of the infall field still exists in space? This remnant would not be powerful enough to cause fast inflation like in the early cosmos. However, it could give the modest push that is propelling cosmic expansion today. Dark energy could be the final breath of the force that created our universe, still resonating through space after nearly 14 billion years. Imagine the ripples caused by a stone thrown into a perfectly motionless pond. Long after the stone has sunk and the original splash has subsided, little ripples continue to spread out. Dark energy could represent the final ripple from the cosmic inflation that created our universe. But this is where things get crazy. If dark energy is derived from leftover inflation energy, it should gradually decrease as the universe expands. It should eventually fade away, allowing gravity to slow cosmic expansion. Once again, our current phase of acceleration would be transient, a bridge between the matter-dominated past and an unknown future. Other hypotheses propose that dark energy may be rising rather than decreasing. If this is true, then cosmic expansion will accelerate, faster and faster till it rips apart. The huge tier scenario, which includes galaxies, solar systems, atoms, and possibly space itself, would bring our universe to an end in approximately 22 billion years, when expansion grows so intense that the fabric of space-time itself is ripped. Alternatively, dark energy could oscillate, pushing and resisting growth. This could result in cycles of acceleration and deceleration, perhaps leading to future periods of cosmic contraction and fresh Big Bang occurrences. The most troubling idea is that dark energy indicates a fundamental instability within the quantum vacuum. Our current vacuum state could be a misleading vacuum, temporarily stable, but will eventually degrade to a lower energy state. When this occurs, a bubble of real vacuum expands at light speed, killing everything in its path and rewriting the laws of physics. This vacuum decay could have started somewhere in the observable universe. The destructive bubble would remain invisible until it arrived. We would never see it coming, as it travels at light speed and erases reality as it grows. Dark energy pushes us to consider the idea that our universe's seeming stability is an illusion, a brief respite before an impending storm that may transform or destroy everything we know. The universe appears to be intended for human existence, and no one understands why. You are alive today as a result of the most extraordinary cosmic coincidence known to science. The factors that regulate reality are so well balanced that altering any of them by even a small bit would render stars impossible. Atoms are unstable, and any type of complexity is strictly forbidden. Consider gravity to be the weakest and most fundamental force. If gravity were even slightly stronger, stars would burn through their fuel in millions of years rather than billions of years, allowing no time for evolution. If gravity was somewhat weaker, stars would never form because gas clouds could not collapse under their own weight. If the electromagnetic force were stronger, electrons would attach so strongly to atomic nuclei that chemistry would be impossible. Making it weaker would cause atoms to fall apart, resulting in molecules and complicated structures that physics forbids. The strong nuclear force that keeps atomic nuclei together may be controlled much more accurately, with changes of only 5% in either direction. And you remove either carbon or oxygen from the universe. Without these elements, the chemistry of life is impossible. However, the most surprising example is the cosmological constant, which generates dark energy. As previously explained, quantum mechanics predicts that this constant should be 10 to the 120th power, bigger than observed. However, it is tuned to virtually exactly zero, allowing the universe to exist for billions of years, rather than expanding so rapidly that stuff cannot clump together. The chances of all these constants randomly falling into the restricted ranges that allow complexity are almost zero. It's like firing a dart from a million miles away and hitting a target as little as an atom. The likelihood is so low that it may as well be impossible. This fine-tuning dilemma compels us to consider unpleasant questions regarding the nature of reality. Did someone or something purposefully set these constants? Is our cosmos structured to allow consciousness and complexity to emerge? Most physicists reject the concept of intelligent design, but they are left with equally mind-bending alternatives. The multiverse hypothesis proposes that limitless universes exist with random physical parameters. Most are sterile wastelands, yet we see a finely tailored universe since we couldn't exist in any other kind. The anthropic principle takes this theory a step further, claiming that the universe must be compatible with consciousness because conscious observers are present to study it. We don't see random physical constants since they don't typically produce observers. Yet some physicists argue that awareness itself, quantum measurement effects, may play a role in the selection of physical constants. If observer moments aid in the collapse of quantum possibilities into definite realities, then the act of observing may physically adjust the cosmos to accommodate observers. This opens up the most radical prospect of all. Consciousness and physical reality co-evolve together, changing each other in ways we're only beginning to grasp. Other worlds might be colliding with ours right now. While you read this, our universe may be colliding with parallel realities in slow motion, leaving delicate fingerprints on the cosmic sky. These collisions wouldn't destroy galaxies or planets. They would happen so gently that only the most sensitive instruments could detect their traces. According to eternal inflation theory, our universe is just one bubble in an infinite foam of realities. Most of these bubble universes expand away from each other faster than light, making contact impossible. But occasionally two bubbles might form close enough together that their boundaries touch before cosmic expansion pulls them apart. When universe boundaries collide, they don't explode like car crashes. Instead, they interact through quantum fields that exist on both sides of the collision zone. These field interactions would release energy that propagates through both universes as gravitational waves and radiation from inside our universe. Such a collision would appear as a circular pattern in the cosmic microwave background radiation, the ancient light that fills the sky from the Big Bang's afterglow. The collision zone would create a subtle, warm or cool spot in this radiation, like a cosmic bruise marking where another reality touched ours. Several research teams have claimed to find such patterns in cosmic microwave background data. Though other scientists dispute these findings, the signatures are so subtle that they're difficult to distinguish from random fluctuations or instrumental noise. We might already have evidence of parallel universe collisions, but we can't be certain yet. If parallel universe collisions are real, they could happen multiple times. As our cosmic bubble encounters different neighbors during its expansion, our sky might contain several collision signatures from different parallel realities, each one marking a brief moment of contact with an alternative cosmos. But here's the truly mind-bending possibility: if universe collisions can happen, they might also be able to exchange information across the boundary. Quantum fields could carry data from one universe to another during the collision process, creating a form of interdimensional communication. Some physicists speculate that consciousness itself might be able to tunnel between colliding universes under special circumstances. If awareness is a quantum phenomenon, as some theories suggest, then parallel universe collisions might briefly connect the conscious experiences in different realities. This could explain certain strange experiences that feel like memories of events that never happened, or déjà vu sensations that seem to come from nowhere. Perhaps your consciousness occasionally receives echoes from parallel versions of yourself living in nearby universes that briefly touched our reality. The implications extend beyond individual experience. Entire civilizations in parallel universes might attempt to send messages across dimensional boundaries during collision events. The cosmic microwave background could contain encoded information from advanced beings trying to communicate across the multiverse. Future technology might allow us to decode these interdimensional messages and send replies of our own, establishing contact with parallel versions of Earth and humanity. We might discover that consciousness naturally seeks connection across all possible realities. Your entire reality might be a projection from a distant boundary right now. As you experience this three-dimensional world around you, you might actually be observing a hologram projected from information stored on a two-dimensional surface, billions of light-years away. This isn't science fiction speculation. It's a serious theory supported by cutting-edge physics and observational evidence. The holographic principle emerged from studies of black holes, where physicists discovered something impossible. When matter falls into a black hole, it seems to disappear from our universe forever. But quantum mechanics says information can never be destroyed, creating a paradox that threatened to break the fundamental laws of physics. The solution came from realizing that information falling into a black hole isn't really destroyed. It's encoded on the black hole's two-dimensional surface. From our perspective outside the black hole, the information never quite reaches the event horizon. Instead, it spreads out across the surface, creating a complete record of everything that ever fell in. This discovery led physicists to a startling conclusion. If all the information in a black hole's three-dimensional interior can be encoded on its two-dimensional surface, perhaps all the information in any three-dimensional region can be encoded on its boundaries. Applied to cosmology, this means our entire observable universe with all its galaxies, stars, planets, and life forms might be information encoded on a distant two-dimensional boundary. We experience three dimensions because that's how the information is processed and projected, but the fundamental reality exists on a cosmic horizon we can never reach. Think of watching a movie on a screen. The movie appears three-dimensional and full of complex action, but it's actually information patterns on a flat surface. The holographic principle suggests our universe works the same way, with all of reality's complexity emerging from information patterns on a distant boundary. This idea explains several puzzles about quantum mechanics and gravity. It suggests that what we call space might be emergent arising from quantum entanglement between different regions of the boundary information. Distance in our three-dimensional world would correspond to the degree of entanglement between boundary regions. The holographic principle also offers insights into what existed before the Big Bang. If our universe is a holographic projection, then the Big Bang would represent the moment when information processing began on the cosmic boundary. Before this moment, the boundary would have existed in some dormant state containing the potential for our reality, but not yet projecting it. Some versions of the holographic principles suggest that consciousness itself might be the projection mechanism, transforming boundary information into experienced reality through the act of observation. In this view, conscious beings aren't separate from the holographic projection. They're part of the processing system that creates the projection. This leads to an extraordinary possibility. If reality is holographic, then the apparent separation between different conscious beings might be an illusion. All observers might be different aspects of a single information processing system, experiencing itself from multiple perspectives simultaneously. The boundary between self and universe dissolves in the holographic paradigm. Time might not exist at the most fundamental level of reality right now. You feel time flowing from past to future, carrying you forward through moments that seem to unfold in sequence. But this experience might be a convincing illusion created by the complex arrangement of matter and energy in your brain at the deepest level of reality. Time might not exist at all. Think about a movie recorded on film. The individual frames exist simultaneously on the reel, but when played in sequence, they create the illusion of motion and temporal flow. Similarly, all moments in the history of our universe might exist simultaneously in a timeless realm with consciousness, creating the illusion of temporal flow. By experiencing these moments in sequence, this idea emerges from STEM.